Hi, and welcome to this new lecture of Mechanics Applied to Aerospace Engineering. Today we are going to cover the constraints of rigid bodies. This will be a complex topic, but an important one for the solution of rigid body problems. After a quick introduction where we will make the connection between constraints of rigid bodies and constraints of point particles, we will cover the topics of constraint equations and reaction forces and torques. Along the way, we will cover a number of examples. Then we will continue with the discussion of friction forces and friction torques. And then we will move on to the rolling without a slip constraint, which is an important one for rigid bodies. To close the lecture, we will visit two different topics. The first one is what happens when we have several bodies or point particles or a combination of both in a system. And finally, what to do when there are reaction forces or reaction torques that we cannot determine, what we call indeterminable reactions. All right, so let us get started. Consider that we have a rigid body. We're going to call simple constraints those that are stationary, integrable, and unconditional at the same time. These are essentially equations on the possible motions of your rigid body, limitations on the kinematics of your rigid body. And in implicit form, we can express them as a series of equations. The number of equations that we need to represent the constraint, let's call that number n, that will be the dimension of the constraint. All right. So the most basic constraint would be a simple constraint with just one equation. That would be a one-dimensional simple constraint. In general, we know that when we have this type of constraints, what happens is that the number of configuration degrees of freedom decreases by n, the dimension of the constraint. Okay, so if we start with a free rigid body in space, that is a total of 6 degrees of freedom, when we consider that we have an n-dimensional constraint, the remaining configuration degrees of freedom is 6 minus n. And therefore, we will need to look for 6 minus n generalized coordinates to describe its configuration. Okay. Of course, at the same time, when we introduce a constraint, we know that we are reducing the number of degrees of freedom, but at the same time, we are introducing extra unknowns. And the number of unknowns that appears is precisely n. Okay, so of course, if you add together these two numbers, you still have 6, which is equal to the number of equations that you have for the rigid body, and the problem remains closed. One of the main differences between constraints on rigid bodies and point particles, which you already know from a previous chapter, is that the constraints on a rigid body can create reaction forces, but they can also create reaction torques. Okay, and in general, they can create either forces and or torques. All right, there will be complex configurations where a single one-dimensional constraint can create at the same time a force and a torque, as we will see later in this lecture. All right, the important thing is that each constraint introduces a total of n unknowns. So a one-dimensional constraint must introduce just one extra unknown in the problem. A little bit more advanced view on constraints is to think again in terms of the configuration space. So if we start with our initial 6-dimensional space for a free rigid body, each constraint will be a manifold on this configuration space. What is a manifold? Well, essentially it is a generalization of a curve, a surface, or other objects in this higher dimensional space. All right, you can call this a hypersurface if you want. So our purpose, and in full parallelism with what we did in 3 dimensions with a single point particle, will be to find or to choose a set of coordinates to parameterize this manifold, which is the locus of points where the body configuration can exist. Okay, and in fact, the generalized velocity vector, which is just the concatenation of the velocity of one point of your rigid body and the angular velocity vector of your rigid body, okay, is a tangent vector to this manifold. And the reactions will be normal vectors to this manifold. right? So the reactions will be normal to this manifold. This is a slightly more advanced view of constraints, but I think it's interesting to try to visualize or at least to interpret constraints in this way. Of course, in this slide, we have spoken only of simple constraints, which is a very important subclass of constraints, but other types exist, as we will see later. So there are also constraints that depend explicitly on time. There are constraints that are non-integrable, which means that we cannot express them in terms of just the coordinates of our problem. They can be expressed in terms of the derivatives of the coordinates. And there are also conditional constraints, which are in parallelism with the point particle case, unilateral constraints that instead of an equation have greater than or smaller than condition. Okay, so let us take a closer look at the problem of constraints. In particular, in this equation, we are interested in the idea of the constraint equations. So to get something more concrete, let us imagine that we have a free rigid body in space and we have 6 coordinates to describe it. Okay, so just to be specific, imagine that we choose the Cartesian coordinates of the center of mass and some Euler angles. We know that if we specify these 6 numbers, we can completely determine the configuration of the rigid body. So if we have a one-dimensional constraint, okay, a one-dimensional simple constraint, we know that we can express that as an implicit form as a single equation. The equation will have the form of some function of the coordinates that we have chosen, okay, so something like this, equal to 0. That's the implicit form of a constraint. If the constraint is simple, indeed we can write it in this form. If it is not simple, and for example it is non-integrable, it will also depend on the derivatives of your coordinates, okay, etc. Also the derivative on the angles. And if it's not stationary, it will depend also on time, and so on and so on. Okay. Well, just to have an example, something that will resemble what you already know from point particles. Imagine that we have a constraint on the position of the center of mass that says that it must remain on the surface of some sphere. All right. Basically, the distance to the origin has to be equal to r. That would be a particularly simple constraint. Another possibility would be to say that the body cannot rotate about 2 particular axes. All right. So this is actually not a simple constraint. This would be a double constraint. We are saying that our body, regardless of how complex it is, okay, we are saying that the rotations about 2 of the axes, for example, the x and y axis, are forbidden. So it may rotate about the 3rd axis, but it cannot rotate like this, okay, or like that. This is forbidden and this is forbidden. Okay, so these are just examples of constraints. This is a double constraint because it has 2 scalar equations. We know that if we can reduce the equation of the constraint to the form that I wrote before, all right, a function of the coordinates only, we can call it an integrable constraint. And these are the easy ones, all right? This is where you can work out with the constraint to reduce the number of parameters, the number of coordinates that you have to express the configuration of your body, and then you can simplify your problem and ignore the equation, okay? When this happens, it is possible to find a parametric form of the constraint, okay? And as I was saying, well, this allows you to reduce the number of coordinates accordingly. When this doesn't happen, well, we have a non-integrable constraint. That's fine. That means that we have to keep the equation of the constraint with us. We cannot reduce the number of coordinates, and at some point we will use the constraint equation to relate the derivatives of our coordinates. Okay, so let's move on to the concept of reactions. And as I said before, we have to consider, in the case of rigid bodies, reaction forces and reaction torques. All right. So these are the mechanisms that make sure that the constraint is satisfied at all times. And they will be as large as necessary to make sure that the body remains in the constraint. Okay. If we have a one-dimensional constraint, this will introduce just one unknown. And this is important, okay? Remember that a one-dimensional constraint cannot introduce two unknowns or anything like that. It will only introduce one unknown. So coming back to the examples of the previous slide, if we have that the center of mass has to remain on the surface of this sphere, the reaction that will appear in this case is just a force applied on the center of mass, which is a radial force, okay, in the direction perpendicular to the sphere, to make sure that the center of mass stays precisely there, just as in the case of a point particle. In the second example, where we were forbidden the rotations about the OX and the OY axis, what happens is that our reaction takes the form of a torque, okay, actually two torques, one about the x-axis and another one about the y-axis. And these torques will be as large as necessary to make sure that the angular velocity projected along these two axes is actually equal to zero, satisfying the constraint. Of course, there are more complex cases. There are cases where a single one-dimensional constraint can introduce at the same time a force component and a torque component. The important thing to remember here is that since it is a one-dimensional constraint, it can only have one unknown. So the force and torque components introduced by it will be dependent on each other. They will be expressible in terms of just one unknown. In general, the force and torque that we have, okay, we can think of that as two three-dimensional vectors that we can concatenate to form a six-dimensional vector. So something like this. Okay, this is our reaction force, and this is our reaction torque, for example, on the center of mass, right? So we have this list of 6 numbers that we can think of as a vector in six-dimensional space. The same thing we can do with the velocity of the point. Okay, for example, the velocity of the center of mass, to be consistent with our choice here, and the angular velocity of the rigid body. So this is another six-dimensional vector. What we know is that the reaction force and torque will point in the direction of the forbidden angular velocity, okay, in the case of a stationary constraint. And this is precisely the normal subspace of the constraint. The velocity, the six-dimensional velocity over here, is a vector that points in the tangent direction of the six-dimensional space. Okay, and again here we are thinking of stationary constraints. So the resulting velocity, it points in the direction that is not affected by the reactions. We know, as we did in the case of point particles, that once we have the equations of motion of the problem, if we project them along the directions of the tangent subspace, the resulting scalar equations will be equations where the reaction unknowns will not appear. So this is exactly the same here. If we select directions that are perpendicular to the reaction force and the reaction torque, and we project the translational or the rotational equations of motion in those directions, the reactions will not appear. So this is perhaps the best way to get rid of them when we are just solving for the coordinates of our problem. If we are interested in the magnitude of the constraints, of course, we want to project in those directions as well. One important thing to remember, and we will see this in the following examples, is that if the constraint is stationary, here's the keyword for this statement, the constraint has to be stationary, the constraint cannot exert any work or any power on the rigid body. That means that regardless of how complex the force and or torque created by this constraint, if we write down the expression for the power of this constraint, okay, which may have some force and some torque, the power has to be equal to 0. All right. So as long as the constraint is stationary, we know that the constraint is not going to exert any work. To illustrate all this, let us go through a number of examples. In this first one, we have this orange bar that is supported against the wall and the floor, as you can see on the drawing. Now, a free rigid body in space would have a total of 6 degrees of freedom, as you know. But this is a planar problem, so we start with 3 degrees of freedom, which you can visualize as the possibility of moving this free body left and right, up and down, and to rotate it about an axis perpendicular to the plane of the drawing. Okay, so of course that would be the case if we had a free body that can move in this planar way. When we consider the constraint, we actually have two simple one-dimensional constraints in this example, because we have that this point A, which is supported against the wall, can only move up and down. Okay, so we are restricting the motion left and right. And similarly for the point B on the floor, this can only move left and right, and it cannot move up and down. Okay, so the way of writing this constraint in implicit form involves a total of two equations, okay, because the dimension of this constraint system is equal to 2. So we have these two equations that you see over here. You see that we have expressed these equations in terms of the coordinates of the points of contact between the bar and the wall or the floor. Okay. However, we usually choose a set of coordinates that may or may not be the coordinates of the points of contact, such as, for example, the coordinates of the center of mass of the bar and an angle, which would be an angle, as you could see over here, to represent the rotation of the bar. All right. So imagine that we start with these 3 degrees of freedom represented with these 3 coordinates. All right. So in principle, if we want to write down the constraint equations, we would have to do that using these coordinates only. Now, this is easy to do in this case because you can find the x coordinate of point A from the x coordinate of the center of mass using the angle psi, okay, and the length of the bar. So if you subtract L over 2 times sine psi to the x coordinate of G, you have the coordinate of A. All right. So the constraint in our coordinates would be written in this form. And similarly, you would do something like that for the other equation. So these would be the equations of the constraint in implicit form in the chosen initial coordinates, okay, for the full 3 degrees of freedom. Now, since we know that these constraints are simple, that means that we can write them in a parametric form. And moreover, we can use them to reduce the number of coordinates, the number of degrees of freedom of the problem, and write everything in terms of just one variable, one coordinate. All right? So we can choose anything. We could choose the angle psi, for example, but in this example, I have decided to use the coordinate xb, which I'm going to call he, okay, the letter and the Greek letter he, as you see over here. So basically this distance, this horizontal distance between the origin and B. So in principle, it should be possible to rewrite all the 3 coordinates that we had chosen initially before applying the constraint in terms of just this parameter. And indeed, we can do so. This has been done over here. This is the parametric expression of this double constraint. And you can use these expressions to replace the initial coordinates that you have chosen over here to express everything on the kinematics of the rigid body in terms of just the he letter. Okay. Observe that we have a number of reactions due to these constraints. We expect a total of 2 independent reactions because we have a dimension 2 constraint. And those are the forces applied on A and B. They are forces that are applied in the direction of the forbidden motion of each point. So since in the case of point A, it cannot move left and right, the force that appears is a horizontal force of unknown magnitude. All right, so that would be the force Fa, as you see over there. And similarly for B, which cannot move up and down, what we have is a force in the vertical direction. In this case, there are no reaction torques, all right, applied at the point of contact. And this is all what you would have for this example. Lastly, observe that these reaction forces do no work on the bar, okay? Since the velocity of A is such that it moves only up and down, it will have a form like, this would be some scalar quantity. It will have a form like this, all right? But the force that we have applied on A is in the I direction. So clearly the dot product between this velocity and this force is always 0. And similarly, something like that will happen with the force Fb. So clearly these reaction forces exert no work in this example. In this other example, we have a sliding collar that can allow the body B2, which I'm going to plot here in blue. Okay, all this part of the figure is body 2, including this collar, that can slide about this vertical bar, which is part of the environment. Okay, we don't care about it. It's a fixed bar, which just represents the constraint. So this is a case where the body can move up and down, and it can also rotate about the vertical axis, right? Any other motion of this rigid body is forbidden. Before we do any discussion of this constraint, it is desirable to do a separate drawing where we eliminate all the graphical complexity of the figure. So I really recommend that you do that in every case. All right, so here on the right, we have drawn the same rigid body B2, which is this blue line over here, and we have represented the collar as just one point, which is the point of contact, the central point of the collar, between the bar and the collar. All right, so this simplified drawing is the one that we want to use to describe what are the allowed and the forbidden motions. So clearly, this point of contact C cannot move in the X or Y direction. These are the first two equations of the constraint. Moreover, the rigid body can rotate about the vertical direction, but it cannot rotate about this axis, okay, or this other axis. All right, so the rotations about X and Y axis are forbidden, and we can represent that by saying that the angular velocities omega X and omega Y are equal to 0. In total, we have 4 equations, and that tells us that the constraint dimension is equal to 4. This is an example of a simple constraint because it can be integrated. Okay, here I have represented 2 of the equations in terms of angular velocities, but you can clearly write that also in terms of Euler angles. So it can be integrated. The equation is stationary in time. The time does not appear explicitly on the equations, and it is unconditional. There are no greater than, smaller than signs on the equations. All right, they are just equal equations. Since we have a total of 4 constraint equations, that means that we can reduce the number of coordinates to describe the configuration of our rigid body B2 to just 2 coordinates. Okay, the number of remaining degrees of freedom is just 2. So we can choose, for example, the vertical position of C and the rotation angle phi, which we have defined here, for example, from the axis Y. Okay. Of course, you can make other choices in what regards the coordinates that you use to describe the configuration of the body. Now, regarding the constraint forces and torques, we see that in this case, we have 2 forces, 2 reaction forces, associated with the fact that point C cannot move in the X and Y direction. So 2 forces, Fx and Fy, appear on C to prevent the motion of C in these directions. Okay? But on top of that, we also have reaction torques, and these are the mechanisms that enforce that the rigid body does not rotate about the X and Y axis. So they are associated to these other 2 equations. All right. So on top of these reaction forces, we have to include these reaction torques. In total, we have 4 unknown parameters: Fx, Fy, Mx, and My, which we have to solve for as part of the rest of the problem. I wanted to do an additional comment in this case. So observe that in this simplified drawing, I have already decided implicitly on the sign of these unknowns. Okay, so when I have Fx that is positive, that means that I have a vector as drawn on the figure. If Fx happens to be negative, that means that the force will point in the opposite direction. And similarly for the rest of the vectors. All right, this is something that you always do when you do this type of drawing. You are choosing what is the sign of your unknowns. Okay, and there is no correct or incorrect choice. You just have to make one. But what is really important is that you must be consistent in your calculations. All right, so if here I'm deciding that fx is positive in this direction, when I make the calculations, it should also be positive in the same direction. That doesn't mean that later on fx cannot be negative or anything like that. It can be any sign. All right. Finally, I also want to make a comment regarding the work of these forces and torques. Observe that they do not exert any work, and this is because the constraint is stationary again. How do we write down the power of this constraint associated to this constraint? Well, that would be the product between fx and x dot, okay, plus fy y dot, plus, for the torques, the power, as you know, is the product of the moment times the angular velocity. So we have mx omega x plus omega y, my omega y. Clearly, this is equal to 0 because in this particular case, each of these terms is individually equal to 0. Okay, what matters for a constraint like this one, a simple constraint, stationary, is that the sum of all the terms has to be equal to 0. All right. In this particular case, on top of that, each of the individual terms is also equal to 0. This is just a variation of the previous case, where instead of a collar that can slide and rotate, we have a collar that can only slide. Okay, here we have a bar, a fixed bar, which is it has a different profile. It has a square section, so that doesn't allow this rotation of the body B2 as before. Okay, so this is also forbidden. That means that the total constraint dimension is 5, and we expect to have 5 equations for the constraint. And indeed, we have the same ones as before, but we have an additional one, which is the fact that it cannot rotate about the z-axis. Okay, this means that the rigid body B2 has only one remaining degree of freedom, so it is possible to represent its configuration in terms of just one coordinate. So in this case, we can choose, for example, the vertical position of the C point, the contact point C. As before, remember that it is desirable to make a simplified drawing without all the complexity of the figure, where we can represent the forces and choose the sign criterion for them. Not just the forces, but also the torques. Expectedly, we have the same reactions as before, fx, fy, mx, and my, but now, since the vertical rotation is also forbidden, we also have a moment about the z direction. Okay, and again, you can check that this system of forces and torques does not do any work on the rigid body because this constraint is stationary. Let us move on to the next example. So here we have two bodies, B1 and B2, which are connected by a pin, as you see on the drawing. This pin forbids any relative motion between the two bodies, except for the rotation about the pin axis. Now, for simplicity, we are going to assume that B1 is stationary, and we are just going to describe the motion of B2 with respect to it. But this doesn't have to be the case. In general, we can have both bodies moving, and then we just have the constraint that limits the relative motion between the two bodies. As before, we are going to do a separate drawing where we eliminate all the graphical complexity of the problem. And here I have selected a reference frame S1, which is a body fixed reference frame attached to body B1. Okay, this is the reference frame that I have drawn in black, and another reference frame in blue, which is the one associated to body B2. All right, so two body axes, two body fixed reference frames, one associated to each of the bodies in the drawing. So as you can see, the center point of the constraint, which is, you can imagine the center point of the pin, that is our point C, it is a common point of the two rigid bodies. It is a body point for the two bodies. The velocity of that point associated to body B2 relative to body B1 is equal to 0. And in fact, in the drawing that I have made over here, I have selected this point to be the origin of the two reference frames. So this constraint, we can express it as 5 equations because it is a 5-dimensional constraint. And these equations are the following. We just have to say that the components of the position vector of point C are all of them equal to 0. Okay, so these are the first 3 equations. And on top of that, the constraint forbids the rotation about the x-axis and the y-axis. So we can also write omega x and omega y equal to 0. Okay, again, a simple constraint because all these equations can be reduced to equations of the coordinates. You can always integrate these last two in terms of Euler angles. All right, so this means that we can parameterize the configuration of body B2 with respect to body B1 in terms of just one parameter, okay, one coordinate. And here we have chosen this angle psi, as you can see in the drawing. All right. What are the reaction forces and torques in this case? Well, expectedly, since we are restricting all possible translational motions of point C, we are going to see 3 forces acting on point C, right? And on top of that, since we don't have the possibility of rotating the body about X and Y, we also see 2 moments of forces, 2 reaction torques at point C. Okay, so these are the 5 extra unknowns that we have in the problem. One thing that I want to mention here is that I have selected to put the force components in the B1 vector basis associated to reference frame S1. But another perfectly valid choice would be to put my forces, for example, on this other vector basis B2. All right, that doesn't affect the problem. That's a perfectly valid choice as well. We just need to introduce 3 additional freedoms, 3 additional parameters. For example, here I have chosen these 3 to represent our reaction force, which we have to solve for as part of the rest of the unknowns of the problem. And once again, observe that since this is a stationary constraint, neither the forces nor the torques exert any work. In this other example, what we have are 2 bodies, B1 and B2, that are connected by a ball and socket. All right, so you can visualize this as a body B2 that ends in this ball here, okay, and a body B1 that has this hole on it, okay, this socket where the ball is introduced so that any rotation is allowed. Okay, this can rotate like this or like that, or even like this. Okay, so all possible rotations of B2 with respect to B1, but the ball cannot go anywhere with respect to B1. Okay, so the motion of this center point C of the ball is restricted. Again, we always do our auxiliary drawing without the graphical complexity. We have introduced a reference frame S1 for body B1, a reference frame S2 for body B2, and they share the same origin, which is the point C, the common point between the 2 rigid bodies. Okay. Now, the constraint equations in this case, I have chosen to write them in a slightly different way, but of course you can rewrite in the same way as in the previous slides. The constraint reads as follows. We are basically saying that the position of point C as seen as a point of body B2 and the position of point C as a point of body B1 have to be equal in another reference frame 0. For example, if you have another reference frame here, which is your reference frame S0. Okay, so basically the point associated to each body that is at position C has to be the same for the 2 rigid bodies. Of course, you can take derivatives of this equation and you will find these alternative equations. Now, if you want to just to describe the motion of body B2 with respect to body B1 as we did in the previous slide, you can refer the velocity of point C as a point of body 2 to body B1, and just say that this velocity is equal to 0, okay? Or, of course, completely equivalent, in the case of the position, you would do this as well. Okay, sorry, that would be 1. So this is the position of C as a point of body 2 in reference frame 1. In this case, we have a constraint that has dimension 3, so we have to choose 3 parameters to describe the relative motion of B2 with respect to B1. And in this case, since there are 3 rotations, we can choose, for example, 3, 1, 3 Euler angles, psi, theta, and phi. The reactions of this constraint are just 3 forces applied on C, because those are the motions that are forbidden. Again, remember that we can rewrite this as xc equals 0, yc equals 0, and cc equals 0. It's the same. Okay, so those are our reactions. And once again, since this is a stationary constraint, it does not exert any work. Finally, let us cover a slightly more complicated example. Imagine that you have this nut, okay, which can move left and right about this threaded bolt, as you can see on the drawing. But obviously, as it moves left and right, it must also rotate because of the thread, all right? So let us see how we can analyze this case. Now, there are some obvious constraint equations that we can write directly. First of all, the motion of the center of this nut in the y and z directions are forbidden. So we can say that yg and cg are equal to 0. Similarly, we know that the nut cannot rotate about the z or y axis, all right? So this is completely forbidden, and that means that the angular velocity omega y and omega c are equal to 0. The difficult equation for the constraint is the last one, which relates the horizontal motion about the direction x and the rotation, which we have represented here with this rotation angle psi. Okay, now when we talk about threads like this one, threads have what we call a thread pitch, which is the amount of horizontal translation that the object experiences for every full rotation. Okay, so the last equation can be represented as you see over here. Basically, a relation between the psi angle and the xg variable. All right. Now, since it will be useful in a moment, let us take the derivative of this equation and write it like this over here. Observe that the derivative of psi is just our omega x, okay, the angular velocity in the x direction. Associated to the first 4 equations, there are these obvious reaction forces and torques, which you can think of them in the same terms as in the previous examples. So I will not dedicate more time to that. Let us take a look at what is the reaction associated to the last equation, which is the more complex one. Okay. Now we can perhaps imagine that this reaction must involve a force in the x direction, but also a torque in the same direction, because these are the directions or the types of motion that are constrained by this equation. All right. The point is, we know that since we are dealing with just one equation here, this constraint force and torque must involve just one extra unknown. All right. So while we have introduced independent unknowns for these other reactions, the remaining reactions associated to this constraint equation have to involve just one extra unknown. All right. So how can we deal with this case? Well, if we represent the constraint equation in the velocity space, all right, the one that you see here in the parentheses, you can see if you plot this equation, so if you plot it in x dot and omega x axis, that the allowed motions are represented by this blue line. Okay, the slope of this line is, well, in this axis is 1 over h over 2 pi. Okay, So this is what tells you how much velocity, when you have some velocity to the right, what should be the rotation of the nut. Okay, this direction is represented by this vector. Okay, this is the direction of the vector of the manifold, or of the curve or the surface or the hypersurface associated to this constraint, to this last equation of the constraint. And we know that the reaction has to be a vector perpendicular to this direction. That vector is, for example, this one. Okay, you see that here I'm not worrying about taking the vectors unitary. That doesn't really matter because we are going to multiply the reaction by a factor in the end. What matters is the direction that I choose. All right. So using this information, the fact that we know that the reaction has to be normal to the constraint, to the equation of the constraint, we can say that this vector, okay, the vector constituted by fx and mx, has to be parallel to this normal vector, okay, the red one here on the drawing. And since we just say that they have to be proportional, let us put here some unknown factor. This is the unknown factor that we were referring to before. Okay, so from here we can solve for fx and mx, and you see that they take this form. All right, and here you can clearly see that they are linked together. They are not independent because they depend on the same unknown variable lambda. All right, so this is a dimension 5 constraint. In total, it involves 5 extra unknowns, the 4 that you have over here plus lambda. All right, importantly, observe that since this is also a stationary constraint, the work associated to it is equal to 0. In fact, if we represent the power associated to each of these constraint equations, they are 0 independently. Okay, because, well, you have the force Fy multiplied by the velocity in the direction y, which is 0. Same for this and this and this, as we have seen in the previous examples. The interesting bit is the one associated to the last equation here. So if you want to represent the power associated to this last equation, you have to consider all the reactions associated to this last equation, which are fx and mx, and multiply them by the corresponding velocities. So here they are. Okay. Now in this particular case, all that we know is that the sum of these two terms is equal to 0. And indeed that makes sense because, well, the force is in this direction while the velocity is in this perpendicular direction. So clearly this, which is the dot product between the force torque vector and the velocity, angular velocity vector, okay, this is just the dot product of these two weird vectors, that is equal to 0. All right, you can check that. But this doesn't say that each of the terms independently has to be equal to 0. And indeed, they can be different from 0. So that means that the force by itself is exerting some work, and the torque is exerting minus the same amount of work. This can be interpreted as this constraint, this last equation of the constraint, as if it were transmitting energy from rotation to translation and vice versa. Okay, and indeed, if you push on this nut to the right, you see that it will not only start moving to the right, but it will also start rotating necessarily because it has to satisfy the constraint equation. And that means that some of the power that you are inputting into the nut will be converted into rotational power, rotational energy. And this is done by the constraint. Okay, the constraint does not create or destroy work or energy, but it can allow to convert energy from one mode of motion to another mode of motion, as it is the case here. All right, so let us move on to something else completely, and let us discuss very briefly the concept of friction. So just as in the case of the point particle, we may have friction when our body is in contact with a rough plane, for example, or another body, and the connection between the two of them is sufficiently rough. And just as in the case of the point particle, we have to consider two different possibilities where the friction forces behave in a completely different way. The first one is when the friction force is below the maximum value given by mu times n, where n is the normal force. So when the magnitude of the friction force is below this value, we don't know exactly how much it is and in which direction it's pointing, and we have to treat it as an extra unknown. Okay, so this is the case where the friction is a reaction force. Okay, so we just introduce an extra unknown value, unknown parameter for this friction force, and we try to solve the problem accordingly. Of course, we have to monitor constantly this condition, because if the magnitude of the force of the friction force happens to become greater than this value, then we will jump to the second case, which is this one over here. Okay. In the second case, we have that the friction force is not involving any extra unknown, so we have to consider it as just another applied force, like gravity, for example. In this case, the magnitude of the friction force is the maximum one, mu times n, and its direction is minus the velocity of the point of contact where the friction force is applied. Okay? Now, in the first case, we know that the friction force exerts no work because the velocity of the contact point is equal to 0, and therefore, since this point is not moving, the force is not doing any work. In the second case, the friction force is opposite to the velocity, which is non-zero, and that means negative work. Okay, the friction force is dissipating energy. Well, so here's the example from before. I have added the two friction forces. We should consider what is going on with the body. If the body is stationary, that means that the velocity of point A and point B are 0, then we have to study this case. If this metal bar is sliding, so basically imagine that it's falling because there is some gravity, so this is moving like that, and this is moving to the right, then the velocity of the contact points A and B is non-zero, so we would be in this other case. All right. Just as in the case of point particles, you have to monitor the conditions for the maximum value of the friction for the reaction force case, and the velocity of the contact point when you are in this other case, to detect when you have to switch from one to the other. Okay, so you basically have to consider two different formulations of the problem and switch accordingly. In the case of rigid bodies, there is a new possibility, which is the possibility of having friction torques. Okay, again, the friction torque would be proportional to the normal force. All right, and well, it would happen, for example, in the case where you have like a ball that is a little bit fluffy or fat. So the point of contact between this ball and this plane is not exactly just one point, but a small area. So this can create some friction. So imagine that you put this ball on the floor and spin it about the vertical, all right? This ball at some point will stop. Why? Because there is this friction torque gradually stopping it. So this could be also a possibility. Again, this friction torque could be a reaction force or an applied, this friction torque would be either a reaction torque or an applied torque, depending on the case that where we are. Okay, if the angular velocity is different from 0 in the direction associated to the torque, then we are in the applied torque case. If the torque magnitude is smaller than some limit value given by the friction coefficient and the normal force, then we are in the first case, we are in the reaction torque case. In the next topic of this lecture, we are going to look at a very peculiar constraint between rigid bodies, which is the constraint of rolling without slip. Okay, so we have already introduced the concept of no penetration. So that was the example of the orange bar supported on the wall and on the floor. There were reaction forces that stopped the bar from entering into the wall or from separating from it. Okay, In general, when we have two bodies, we have to consider that both of them can be moving and they can be translating and rotating. So the condition of no penetration at the contact point C reads as you can see over here, right? So imagine that we have these two bodies that you see on the bottom of the slide. So we introduce two directions, the direction along the normal, that's the direction Z, and the direction along the tangent of the contact plane, which is Y. Okay, so the condition of no penetration means that the difference of the velocity of point C belonging to body 2 and the contact point C belonging to body 1 in the direction of the normal is equal to 0. Okay, if you want to write it a bit more compact, you can write the velocity of, say, body 2 expressed with respect to body 1, and that has to be equal to 0. All right. Okay, well, this is the condition for no penetration, but we are not saying anything about the slip between the two bodies. Okay, the velocity of the contact point of each body in the direction of Y doesn't have to match if we just have this condition. Now, the condition of no slip adds information on this. So this basically says that the velocity of the 2 points of contact has to be equal also in the direction of the tangent. Okay, so when we have no penetration and no slip, we are going to refer to that as rolling without a slip when the body geometries are sufficiently smooth so that rolling can happen. And what we have is that the 3 components of the relative velocity will be equal to 0. Okay, so in other words, we can just write that the velocity of the contact points are equal, or that the relative velocity is equal to 0. Okay, so as I was saying, when the bodies are sufficiently smooth, they will roll with respect to each other. And that means that the instantaneous point of contact, what we here in the drawing are calling CB1 and CB2, will be a different point at each instant of time. Okay, so for example, if at the next instant of time the point of contact has moved upwards, we will have that the new point of contact is this one for body B1 and this other one for body B2. And in order to keep things simple, we are going to save this letter C for the contact point at each instant of time. Just remember that it will be a different point of each body at each instant of time. We are just labeling the contact point in this way. Since if we have a body that is rolling without a slip with respect to another, that means that the distance traveled by the contact point in the same amount of time is the same on one body or the other. Okay, basically they are rotating smoothly over each other, and the amount of length that we travel on one side is the same as what we travel on the other side. This is expressed here with the condition that the arc length S1 and S2 on the drawing are equal. So rolling without a slip is an important constraint because it appears in many applied problems of engineering, also in aerospace engineering. And it is interesting to see that it couples together the translation of the body with its rotation. Okay, so let us take a closer look at a simpler example. Just a disc or a wheel, as you see over here, rolling without a slip over the floor. So the contact point, what we call CB or CF when we refer to the corresponding point on the floor, they have the same velocity. If we accept that the floor is not moving, that means that the velocity of the contact point of the wheel has 0 velocity. Okay, since it is a point of 0 velocity, it is a point of the instantaneous axis of rotation. And in fact, if we look at the equation of the velocity field of the rigid body, using the point C as our reference, we know that since it is 0, we can just express the velocity of any point as this rotational term. Okay, so in this separate drawing, this is our point C, all right, what we have is that every point of the rigid body, if we draw some lines for reference, okay, every point of the rigid body has a velocity that is proportional to the distance of from C, okay, and it moves like that. So this point is moving like that, like that, like that, like that, and so on, okay. So the farther away you are from C, the bigger these arrows become, okay. So at any instant of time, this is the instantaneous photograph of the velocity field of your rigid body. Okay, of course, as the body moves, the point C will be another one, and the velocity field will be, well, identical to this one, but about that new point. The coupling associated to this constraint means that when the disk moves to the right, it also has to rotate. Okay, and the condition using the velocity field equation of the rigid body, particularized at the center of mass of the rigid body, and taking into account that the angular velocity vector can be expressed in the direction of k0, actually in the direction of minus k0, then the condition is this one. Okay, so this is again just the particularization of this when P is the center of mass G. Okay, and solving this cross product, which of course is very simple. Jk 0, 0 minus omega, and the vector Cp is this vector, okay, Cj in this case. So Cj is 0 r because it's the radius of the disk. This is the distance from C to G, and 0. Okay, so if you take this determinant, well, in essence, this is what you find. This is the connection that exists between the horizontal velocity of the center of mass and the rotation of the disk. In this case, the rolling without a slip constraint can be integrated, so it becomes an integrable constraint. This is what I get if I integrate in time and I say that theta dot is omega. Okay. However, in more complicated scenarios where we have, for example, a disk that can rotate over a plane, but not in a planar, like in this planar problem, but in 3D, then we will see that this is a non-integrable constraint in general. Okay, so this is one example where you cannot integrate all the way to the coordinates as we can do when the problem is planar, as in the case of this slide. More important things, well, the reaction forces at this contact point, we just have reaction forces, no reaction torques. So we have a normal force pushing the disk away from the ground, okay? And in general, we also have a friction force. So let's call this force N in the J direction, and this will be the friction force Fr in the I0 direction, like this. Now, we don't know what is the value of either of these unknowns until we solve the problem. Perhaps it's relevant to make a comment about the friction force. We don't know in which direction is pushing the disk. In general, it can be to the right or to the left. It really depends on what the disk is doing. If the disk is accelerating, for example, the friction force will point forward. If the disk is decelerating, it will point backward. Okay, and it can also be 0. If you just set the disk in motion with the right velocity and it is not accelerating, there is no need to have any friction force to keep that condition going. So it can also be that you find that the friction force happens to be 0 for your problem. Okay, now as in any other case where we have friction, it is important to monitor the condition for having the friction as a reaction force. So if the disk does something unusual, for example, it tries to accelerate very quickly, the friction force necessary to keep the rolling without a slip condition may become too high and the disk may begin slipping. Okay, this is what happens, for example, when you have a car and you hit the pedal very far and you try to accelerate very quickly. The wheels of the car can skid on the road. They will begin to slip, actually. However, if you accelerate slowly, this will not happen. there will be no slipping. So as long as there is no slipping, we can check what is the power done by the constraints of this problem, the rolling without a slip constraint. So we have n in the direction of the vertical velocity, which is 0, so that force does not create any work. And the same happens with the friction force. As long as the velocity of the contact point is 0 because there is no slipping, the friction force does not work on the disk. And that is important, okay? So as long as the friction force is a reaction force and the contact point velocity is 0, the friction port does not exert work, all right? However, whenever there is a slipping, the friction force will create negative power. Okay, so it will dissipate power from the system. Another interesting way to see this power and work condition is to consider the system of forces created by N and F and reduce this system of forces to the center of mass G. Okay, remember that this is something that we can do always with any set of forces, including reaction forces. So the reduced system is the resultant force, which is N plus Fr, and the torque about G. The normal force does not create any torque about G, but the friction force does. And this is the torque associated to the friction force about the center of mass, right? So another way of writing the power associated to these two forces is to use the reduced system of forces on the center of mass using the velocity of the center of mass and the angular velocity of the rigid body. So the same thing that we did over here, that this is the expression of the friction force if we take the point C of contact as our reference. Okay, so there is no torque about C, so we just have the resultant force multiplied by the velocity of C, and we know that this is 0 as we saw before. Another possibility is to use the reduced system of forces about G using the velocity of G and the angular velocity of the rigid body, and this is what we get. And of course that also has to be equal to 0 because this system of forces we know that is not creating or destroying any energy. Now, the interesting thing of doing this is that we now again see two terms. Since the sum of these two terms has to be equal to 0, this means that, well, the sum is 0, but each of them doesn't have to be 0 independently. Okay, so this means that with respect to the center of mass, the friction force can be accelerating the velocity of the center of mass because it is creating positive power for this term at least, but it may be creating negative power regarding the other one. Okay, so again we have that this constraint, the rolling without a slip constraint, works as a mechanism to convert rotational energy to translational energy. Okay, and again the example of the car is very relevant. What happens really when you hit the pedal of the car trying to accelerate? What you do is you impress a torque on the wheels to try to make them spin, okay? But the friction force, which will be in the direction forward in that case, converts some of the energy that you transmit to the wheel to make them rotate, so rotational energy, some of that energy will be destroyed by this friction force, and it will appear over here as translational force. And that is what makes your car to go forward. It is the friction force of the wheels with the road, which point in the direction forward, all right? So they appear in your resultant force, all right? And that is what will move your car forward. In essence, the total energy that you have is split into some rotational energy for the wheels and some translational energy for the wheels. Well, and for the rest of the car, of course. All right, so this is an interesting interpretation of this equation. The constraint is allowing you to transform energy from one mode to another, a different mode of motion. All right, so to conclude this lecture, I just want to go through two additional topics. One of them is what happens when we have several bodies or bodies and particles and so on. So we can regard this as a problem where we have more degrees of freedom, more configuration degrees of freedom. As always, we can define our configuration space. In that case, when we have multiple bodies and point particles, it will not be a 6-dimensional space, it will be a much higher dimensional space. But the same concepts that we have introduced in this lecture, and which are in essence the same concepts that we saw in the lecture of the constraints of a point particle, apply also on that case. So as I was saying, we can still define a configuration space with as many dimensions as configuration degrees of freedom. Okay. Now, each one-dimensional constraint that you have on your system, which may link together not just coordinates of each individual body, but coordinates of several bodies and several particles at the same time, can be regarded as a manifold, a one-dimensional manifold, a one-dimensional constraint on this high-dimensional configuration space. The constraint reaction will be a generalized vector perpendicular to this object. Okay, and in general, it will be a combination of forces and torques on all these particles and bodies of your system. When you have two bodies, for example, B1 and B2, you have to remember that thanks to the action and reaction principle, the third law of Newton, we know that whatever the body 1 causes on body 2 is equal and opposite as whatever the body 2 causes in body 1. This is why it is particularly important to draw what I call an exploded view of your system, okay? To try to understand what is the sign criterion of your reaction forces and reaction torques on each of the constituents of your system. So just to put a very quick example, imagine that you have a system composed of two rigid bodies, these two bars, which are connected at this pin connector over here. Okay, and imagine moreover that this is a planar problem for simplicity. So what do I mean when I say to create an exploded view? Well, I basically mean draw each body independently and separate it from the rest. Okay, and it is in this diagram where you want to draw your forces and torques, and not on this one, because in this one is very ambiguous. What happens if I put here a vector? Which body is receiving this force, the red one or the blue one? So in order to avoid this ambiguity, draw the body separately and draw the forces and the torques on each of them. So here, this is the point of contact between the two bodies. You see that I have drawn the same reaction forces Fx and Fy on both of them, but with opposite directions, to reflect the fact that they are action and reaction. Okay, and this is what defines my sign criterion when I write down the equations of motion of each rigid body. Okay. To conclude this lecture, I want to make a comment about cases where there may be more reaction unknowns than we can solve for. Okay, remember that a rigid body has 6 degrees of freedom only. Okay, and we have 6 equations for that body. Well, that means that we cannot really impose more than 6 independent one-dimensional constraints on it. If we want to impose a 7th equation of a constraint on the rigid body, well, the body is already fully constrained. That last equation will do nothing on the rigid body, and moreover, we will not be able to determine what are the reaction forces associated to it. And this creates an indeterminacy that can only be solved with more advanced tools than what you will learn in this course. Okay, in essence, that means that we have an hyperstatic condition. All right. And the classical example to illustrate this is to consider a table with 3 legs or 4 legs. Okay, when you have just 3 legs, the equations of motion of this body, which if it is stationary, they reduce to the equations of the statics of this body, allow you to solve for these 3 forces. Okay. When you add a 4th or a 5th leg to the table, in this case, you are not able to determine the value of all the forces. All right. So this happens even if you don't have 6 constraints, because the 4th constraint that you are adding here is already redundant with the 3 constraints that you already had with 3 legs. All right. So this hyperstatic condition may happen even with less than 7 constraints. Okay, they may happen sooner. They may happen sooner. Now, what do we do to solve these situations? We need a flexible body model, which, as I was saying, it is beyond the scope of this course. All right, you will learn about this in future courses. Now, indeed, if you really think of a constraint in a realistic case, you will notice that this happens always to some extent. Okay, imagine that you have a cylinder supported on a plane. Okay, this cylinder unavoidably will not be exactly smooth. There will be some irregularities in it on its surface and also on the floor. That means that there will be a pressure distribution, as you can see here on the right, that is uneven and impossible to determine from the formalism of rigid bodies. You need a flexible body model to determine this distribution, okay? And you need to know all the details about the geometry. So basically all that you can do is to reduce this distribution of pressures to a resultant force, okay, and if anything to a resultant torque, okay, and that's the best that you can do about some point P. All right, that's the best you can do. You can never have more reactions than 3 forces and 3 torques between one body and another. All right, that would be the maximum. And you can see in this example that even sooner you can have problems of hyperstaticity. Okay. All right, so that's all for today. Thank you and see you next time.